Swayam Prabha. Digital India. Educated India.
So let us look at the things in now a little bit more detail. So this is where we started with, and then I was saying that there are these many failure mechanisms, and some of these failure mechanisms are more important than the other one, which I think we'll look a little bit more detail. And especially I mentioned that this is this electrolytic cell formation and the corrosion related to that is much more important, because this immediately create the functional issues, because there is a if there is an electrochemical current, it is a stray current, and that itself will affect the functionality of the electronics. And if there is a dendrite formation between these two, and then it is totally bridging the creating a short circuit and also a problem. So this is significantly this is more important than this one, because this can create intermittent functional issues within a very short period of time. So if you look at some of these failure modes, which a little bit more in detail. So the first thing is, what happens is that when you have the water film formation, so this is this we can take it as without any water film on the PCB surface. If you take it just a small part of it with a positive bias and negative bias, you can have a current through the laminate depending on the bias level here, and current through the surface. And this current through the laminate is very, very low, because this laminate has a very high resistance. So in the normal circumstances, the current through the laminate is very, very low. And this surface water film is also very, very thin. So the current through the surface is also very, very low. So this I1 plus I2, if you take, is very little, that it will not interfere with the functioning of the electronics. But when the water film build up, you build up this I3 current, that is electrochemical current caused by the electrochemical reactions here and electrochemical reactions here, anode and cathode, and that create this electrochemical current. And that electrochemical current will start interfering with this functionality here. Just think that this is a resistor, and this water film on the top forming and creating an I3 current depending on the resistance of this water film. So this part is acting as a parallel resistor to the resistor on the top of that. It's acting as a parallel resistor. So this resistor has to be 1000 ohm. Because of the water film on the top of that, the water film is acting as another resistor. Now the parallel resistor, if you add, the resistance will drop down, and that way it will affect the whole things in the functionality of the device, and system will start showing the faulty signal. So there itself you can get the failure, this I3, because of the I3. That's what we call it as a leak current failure. It is simply the leak current which is caused by the electrochemical process, and that can fail. This leak current has a limit, because when the leak current is happening, metal is dissolving. In addition to electrolysis, the metal is dissolving. So that means that this cannot go on just like that. There is a limit for that. And that limit, when this crosses, this metal ion dissolved will go and deposit here. And there are certain dynamics related to that, mass transfer issue and all. And then you form this dendrite, and then you get an electric short. So we can say that this is a second level failure from this. That's a first level failure, and this is a second level failure. And there is also some kind of boundary here, because this I3 can be maximum 10 microampere, because then it leads to this. We'll see that later. But depending on the sensitivity of the electronics, this I3 is enough to cause a failure. But some electrons which are not that sensitive to the stray current, then you need to go to this level to get the failure. Now the another type of failure, there are many, but I'm just taking these three. Another one is that this polymer laminate this is a polymer, right? So the moisture also can go in. All polymers will absorb moisture. Sometimes these PCBs are made multi-layers. Multi-layers means in order to increase the number of components on the top, and you also put the components on the bottom, and then to increase the number of components at the top, they put some of the conduction lines inside the laminate. So their conduction lines is embedded in the laminate. We'll see that some picture later, embedded in the laminate, and so that they can put more component here. So that means that when the moisture is going in, there can be a copper wire assisting like this inside the laminate. With a this polymer is made of glass fiber composite. So there may be a glass fiber sitting like this. So when this little moisture is corroding the copper, this copper will be pushed, copper product. So since it is a very little water and it's inside the laminate, it will not form like a dendrite, but it will immediately form some copper corrosion product. But this copper corrosion product will be pushed through the interface to here, and then you form a layer. And this layer is not as conductive as this, but that one becomes conductive because of the copper corrosion products are semi-conducting. So then you get a failure, that is what is called this conductive anodic filament failure, which is inside the laminate. And this problem is also increasing because again, this is a function of the bias. So if you have a higher potential, you can have a higher field to push the ions and things like that. And that way this problem is also increasing. So just then take a little bit more on that. So if you look at the water film buildup, so we study the water film buildup on the PCB surface by using different techniques. You will see that technique later. So if you look at here, there's a time here. There's a time of condensation. You can take the time of condensation as water film thickness, because as you cool down, there is more and more water film is forming. And then while that water film is forming on a PCB surface, and which is not this type of surface, but you will see that later, it is like you have an interdigitated pattern like this. So that's a substrate which we use for study. There is one leg like this is connected to anode, and another one is like this, which is connected to cathode like that. And when you form the water film on the top of that, what we are doing is, as the water film is building up, we measure the impedance, and we measure that you apply a voltage, and that creates a DC current, like what you have seen earlier, this I3. And instead of that, we can say that we don't apply a DC, but you do an impedance between these two and measure the impedance with a low voltage amplitude. And we take the full impedance spectra, although I have shown here only impedance corresponds 100 kilohertz. So that's just taking a 1 point from that, but we collect the full impedance spectra. But it shows you that how the water film is forming and increasing the electrical behavior. So as you can see here, when the water film thickness is very, very low, you don't get any appreciable change in the, you don't get any appreciable which one is impedance. So that's impedance. So you get a very high impedance level, and you don't get an appreciable change in the leak current. This blue is not blue one, this black one is the leak current. You don't see much change in the leak current. But then you come to a point here, suddenly you can see that leak current is increasing. Correspondingly, the impedance of the water film is decreasing. But if you look at the phase angle here, you can see that here the phase angle for the water film from the impedance is around 90, and that shift to almost 0 when you have this condition. And what it shows is that is from the impedance, that phase angle, if you look at it, at some particular water layer thickness, this water film is becoming resistive. So earlier it was water film is more capacitive. This water film will have a capacitance and resistance, but it's more capacity dominated because the water film thickness is very low. But at some point of time, the water film thickness is enough, it changes to resistive mode. There the ion conduction occurs and start giving this I3 value higher I3 value, and which lead to the failure. What is this transition point? We will see that later. What is the transition point? So what it tells us that is, if we can keep the water film thickness lower than this value during their condensation regime, you never lead to the failure. Only if you cross that regime and you lead to the failure, But if you keep that value below this regime, always when you have the condensation, you never lead to the failure. That electrical property, what we are talking about, the water film, it's not just for the electronics, it is also important for any corrosion. Think that about corrosion is taking place in the atmospheric condition, and you have a metal surface, a thin film of water is forming. You have anode and cathode, manganese sulfide and steel surface. This manganese sulfide and steel surface is coupled together, and you need to pass a current between those two to corrode. I think that's valid there as well. What water film thickness, you get an appreciable amount of corrosion. I think this is valid there as well. That whether the behavior difference between the capacitive water film and behavior difference between the resistive water film. Because the ion transport is possible, what level of ion transport is possible in the water film depending on the thickness. I mentioned here, this is, you have to assume it as a water film thickness, but I'll show you the outside water film thickness later. But that's one of the results which is really good for us to understand, because then we know that there is a cutoff limit. It's not like you are, as long as the water film is forming, the failure is building up. There's a transition point for the failure at which you get the failure and you don't get the failure before that. All these are, we are trying to understand this water film and how that is building up more and more. So then I also mentioned here, the leak current failure occurs if the system is sensitive for low levels of parasitic current, that is this I3, and that is about 10 microampere. Why we call it as 10 microampere? That's again, there is a cutoff limit. That means that the leak current, this I3 value goes beyond 10 microampere. We are pretty sure that that will lead to this electrochemical migration what we are talking about. This is the difference between we do the work and the power electronics people do the work. Power electronics people won't understand all these differences. We can, now the thing is that we know that where there is a clear boundary between I3 is acting as I3 and I3 is leading to the electrochemical migration failure. We will elaborate on that as we go on. Now first, before we go to that, let us take a little bit on this. That is, this dendrite is forming. There are certain characteristics related to this dendrite as well. Because this dendrite formation, how dense this dendrite, how fast it forms, it also depends upon the distance. Because the electric field between this one is V by D. So as the distance decreases, you have a more electric field, and which means that the field distribution here also becomes little bit more uniform. So if you have a closer thing, you form much more wider dendrite. If you have a far away things, you form much more narrow dendrites and things like that. So the field has a very clear effect. As the distance is decreasing, you have a higher and higher field in this case. So that has a clear effect. But that is one part. The other part is, so we can also do this. So somebody was asking that how we do the experiment. So just one way of doing the experiment, like we have cells like this, we can load one component and then we can apply a bias, and then we can put a small amount of water here, or we can put this entire setup into a climatic chamber and we can cool down and create a condensation on this component. So both ways we can do, and so that we can do this experiment at single component level, we can do this experiment. So that's what you see here. When you do the experiment like that, you get a potentiostatic curve like this. There's a leak current. So that leak current is the current through the water film, I3, which I was talking about. That is, this current is equivalent to this I3, what I'm talking about. And then what will happen is, at some point of time, dendrite will start growing. Then it bridges like that. And then you get a sudden electric short and increase in the current. Things follows after that. The dendrite will burn off and all those things. Or we can do the experiment like this. We have this kind of printed circuit board we make. This is with a lot of components, but sometimes we use only this part. We have the PCB alone, that one. That PCB is, as I mentioned, that look like this. There is one comb part is anode and other one is a cathode here like that. So there are different, we have many designs like that, and that's why we use it as a test systems and applying the bias between these two. And so this particular PCB also has a many components with different sizes and things like that. That's what you see here. That is decreasing the components become smaller and smaller. This time to failure decreases because it can easily form the dendrite and things like that. That is something. But that's not the thing I want to focus. So, one interesting thing is that if you keep increasing the bias, so you think that you are taking a one particular pitch distance, one particular component, and you are increasing the bias, and you then calculating, doing many experiments and calculating the probability for electrochemical migration, that dendrite formation. What you see is that you really see a curve like this, that is going up and decreasing. Like this, you can see a bell curve more or less. You can see that without any contamination, without contamination, things like that, you can see that bell curve here. Interestingly, you also calculate the dendrite current. What is dendrite current means? When this is shorting, what is the amount of current this dendrite can take? That's the dendrite current. Why that is important? Because that current, what is passing the dendrite, that is what is determining how it is burning. So that dendrite current, if you look at it, that also shows a bell curve. So both cases, if you take it, the probability of electrochemical migration shows a bell curve, and the probability of this dendrite formation also shows a bell curve. Why I am stressing this point? That is very important, because why that is happening is again there is a lot of things to do with this stability and pH changes. That is what is happening. So basically this is what happens on the, so now we are taking a component, you are applying a bias, so you have the electrochemical things happening on the surface, tin is dissolving, right? All these are happening, but tin dissolution is not the important thing. In addition to tin dissolution, you also have the electrolysis of water. That electrolysis of water is creating an acidic condition on the anode side and alkaline condition on the cathode side. You can see that as the time proceeds, you have a acidic region on the created by the electrolysis on the anode side, and an alkaline region created by the electrolysis on the cathode side. Which means that in that thin film of water, you need to imagine that because of the field, tin ions are dissolving and moving in this pH condition, crossing to the alkaline condition and coming and depositing here. And that means that if you look at the Porbea diagram, the stability of the tin ions are an important factor as the ions move from the anode to cathode. Because in the anode, you have the tin 2 plus or tin 4 plus, stannic or stannate ion, and then it goes through the neutral pH region, very sharp neutral pH region somewhere here in between, and then it crosses to the alkaline region where tin becomes stannate ions, and this stannate ions is the one then that is depositing on the surface like alkaline deposition of tin. We know that alkaline deposition of tin in the electroplating, like alkaline deposition of tin. And that mechanism is occurring, that's very clear. You see here. Here we can see that you see a kind of a reddish color, and you see a color like this, and in between you have a white color. So that means that tin ion started moving like this. It came across this very sharp neutral boundary where the tin is precipitated as hydroxide, and then this tip of this neutral boundary, you have an alkaline condition here, so that tin hydroxide is dissolving back into stannate ion and then coming and depositing here. Now if you think, that is, all these boundaries are concentration dependent, right? Think that your power is, voltage here is very high, you are dissolving so much tin. This boundary is shifted to here, so that means that even that alkaline condition is not enough to dissolve this tin hydroxide. So tin hydroxide becomes all over the surface. So here if you look at it, that's a sharp boundary like this created. When we stop the experiment in between, here we can see that it is somewhere between shifting totally into here, because you can see a mixture of tin hydroxide and dendrite. So that means that this sequence of events which is happening depends upon the stability, and that stability is depend upon potential and bias and things like that. That has an implication, because so that is this is showing just the modeling showing that it is like how the tin stability changes with the pH and things like that. What is the implication of that? That is the one what is causing the dendrite resistance. So dendrite resistance is a function of different parameters. It is coming because of this local pH changes, how the tin stability is occurring in that solution layer, and that is what is determining the dendrite resistance. And that's what you see here as well. Like you can form the dendrite at a different voltage, and then you can analyze. You can see that some cases you get a much more metallic dendrite compared to that of other cases. You have metallic dendrite which is mixed with the oxide, because tin hydroxide, you can see that is tin hydroxide depositing on the dendrite. You see this TM picture, you can see that this is tin hydroxide. There is a metallic dendrite, but which is covered with tin hydroxide. So when you have the metallic dendrite mixed with the tin hydroxide, you get a higher resistance. That is having implications, because as I told earlier, because that determines the dendrite burning, what kind of spark you get here, and all those things. So the point I'm saying is that there is a lot of things which we need to understand when you are increasing the voltage. So all these things what I'm talking about, you can see that the maximum is 12 volts. The question is what happens with 100 volts, 200 volts, 1000 volts, and what happens when you have the humidity and gases. And this is a new scenario which we need to understand. But that level of that kind of this is an important thing to understand. So that's what I mentioned that earlier. That is when you go to the high voltage, and all these things becomes more important. Now I mentioned that this is a transient effect. So the question is also that, like now in this particular case, for example, in this particular case, when we do the experiment, of course we put a droplet of water on the top, and then, but if on the other hand, when it is in the actual condition, when it is exposing, you form a condensed water film. And this condensed water film, how that is forming, and all these things are also important thing. So if you want to reduce this condensation, water film formation failure, then of course we need to understand how the water film is building up on the PCB surface, what are the influencing parameters. Then by controlling that influencing parameters, how we can reduce the water film formation, things like that. So one of the things, as I mentioned, that the water film formation is occurring on the PCB surface easily, because there is a process related contamination which is coming from the soldering process, which so during the soldering process they use some chemical flux. This chemical flux contains weak organic acid like malic acid, glutaric acid, and things like that. And some of these acids have a lower critical relative humidity. Some of these acids have a higher critical relative humidity, deliquescent humidity. For example, if you have sodium chloride, the deliquescent humidity level of sodium chloride is 75%, meaning that sodium chloride will not absorb moisture until the humidity level is 75%. This is a very important thermodynamic parameter in relation with the deposition on a metal surface. And so when you take these acids which is used in the flux chemistry, like glutaric acid, adipic acid, or succinic or malic acid. Malic acid is very hygroscopic. It can absorb moisture, say at 75 to 80%. Glutaric acid is another one which can probably absorb humidity from 80 to 85%. But on the other hand, this one will absorb humidity only at 98%. So that means that if this contamination on the PCB surface up to 98%, you don't have to worry about condensation. But here you have to worry about condensation when the humidity level is more than 80%. So the humidity boundary itself is determined by the chemistry, what they use in the processing. This is a new understanding in the industries. So now they use better chemistries, so that they can make just by using the better chemistries, instead of this chemistry, if they use this chemistry, then they can change the humidity boundary to 98%. So that's one of the key things that is causing the water film formation, assisting the water film formation. Of course, even without this contamination, if the PCB you cool down, you form the condensation. But the thing is that maybe in that case, the PCB has to be very cold. An appreciable condensation is forming when you have a transient condition, not fully because of PCB is cold. PCB may be a little bit cold, but this one is accelerating that process. So that's the importance of this to remove this. So you can see that is, if you take all these different organic acids that is used in the flush system, it has different this delicacy humidity level around 99%, starting from that. When you go to these acids, it comes to around 80% and 85% like that. So that it is it's a very important thing. So now with that, try to understand clearly that how much water film is forming and what is the nature of the water film. So what we do is that we try to quantify the water film, and at the same time we do the electrical property measurement. So what we do here is that we made an equipment where we can load this kind of test structures. So this is one of the test structure. We can see that there is this comp like this. So we can load this into this equipment, and we can cool down the surface, slowly build up the water film, and while building up, we can measure how much is that quantity by weight from here, and then that weight can be converted into an average water film thickness. Why I say average water film thickness? Because you know that when the condensation is forming, condensation will not form as a uniform layer. Condensation will form as droplet like this, and then the droplet will coalesce together. So smaller droplet forms, and then the droplet coalesce together. And again, I'll tell you that many of these things what I'm talking about here, it is not just for electronic corrosion. It is also important for any atmospheric corrosion, because this is the way it is happening. So that's the reason that I am saying that average water film thickness. So take an example here. So we put that sample, and one of the sample we put very clean. We cleaned everything. Other cases we put these two acids similar to that of the flush residue, which you can see it on the PCB surface, where adipic acid is the one which I mentioned earlier that has a very low hygroscopicity. That means that it can withstand up to 98% humidity. Glutaric acid is the one which I mentioned that there's a very high hygroscopicity, can withstand only 80 or 85. Now we do this experiment, we cool down the substrate. So you can see here this time cooling. Then once the water film is formed, then we heat to evaporate that. So you see the effect here. One is that is, if you have a clean surface, in a full condensing condition, when you reach, you form around 4.5 micrometer of water film. It's quite thin still, 4.5 micrometer of water film you form. If you have adipic acid, because adipic acid is very less hygroscopic, and that also is almost like clean surface, which will not change much the water film thickness. But if you have the glutaric acid on the other hand, it forms almost a double amount of thickness of water film, around 8 micrometer. That's one thing what you see here. Another thing what you see here, when you're cooling down, this is a point at which, you have a PCB temperature, you have ambient temperature. When you cool down at one temperature, this PCB temperature which reaches a dew point. There only the condensation starts. This is that dew point temperature. So what you can see here is, until you reach to dew point temperature, even though there is 98% humidity or 95% humidity, water film thickness is still very, very low. Appreciable water film thickness forms only when the condensation is occurring, and there only it starts affecting the electrical property. Appreciable electrical property, I will come to this. It will start affecting the electrical property. So now you have this water film thickness. Now we can take this one and compare with this. Same time, we measure the leak current between these two and also the impedance. So you can see that as the water film thickness is changing, this follows the same profile. Leak current is increasing and leak current is decreasing and coming down to the original value when this evaporates. You can see the difference here. That's a clean one. That's with adipic acid, this one, and this is with the glutaric acid. So one interesting thing you can see here, water film thickness point of view, whether you have a clean substrate or whether you have with the adipic acid, is the same. But once it comes to the electrical property, there is a difference. That's because on a clean surface, when the water film forms, there is no conducting ions. Glutaric acid, although it will not absorb moisture, but once the moisture forms, it will dissolve into the water film and gives a conductivity, and that increases the leak current. Now we can see the glutaric acid gives much higher leak current. Not only that, leak current is very, very high here, almost reaches to 1 milliampere. And you can also, this fluctuation that is showing that there is a failure, that is electrochemical migration failure and dendrite forming and things like that. That's what happens in this case. So you can see that now what we can do with this, each water film thickness, we can get the electrical property. How I can use this, because you will see the later, because we make the electrochemical model, and electrochemical model, we can calibrate that electrochemical model with these values, because we know the electrical property, not just leak current, but we also know correspondingly the impedance. So impedance also shows a similar thing, that is with the clean PCB, with adipic acid and glutaric acid is dropped the impedance, so it corresponds to this one, you also get the impedance. So we have the full calibration of that water film thickness. But you can see nicely that the water film build up and how that is affected by this contamination, what is the amount of water film thickness changes and like that. Now where we go from there. So the point is that, like one is, this understanding is important for us, as I showed here, because we know that there is a transition point, as I shown that earlier curve, if you remember, which corresponds to this one. We know that there is a transition point, and that transition point is the one also you see here. That transition point corresponds to this. Below that, there is not much effect, and that transition point almost corresponds to this. Now where we go from this. So first thing is that we can use this data, and we can take that kind of structure or any PCB structure and put into an electrochemical model, and that way we can model the current between these two different conduction lines. We can model it, so that we have a calibrated model according to the water film thickness from this one, so that the whatever these leak current predictions what we are making between different points, we can believe that. So that way we can make the electrochemical model. But that alone will not serve the purpose, because the reason is, now there is a little bit more complication, because here we are assuming that this water film thickness is uniform. But water film thickness is actually like this. If the water film thickness is like that with the droplet, is there an implication? Yes, there is an implication, because that implication you can see here. So when the water film is forming, you form like a droplet with an inter-droplet thickness. This inter-droplet thickness is much thinner than this one. You can imagine, right? A droplet, then in an inter-droplet thickness, then another droplet. So the inter-droplet thickness is much thinner than the droplet. So that means that the current which is transported through the film is not dependent upon this one. That's a limiting factor. So that is what determines the impedance, overall impedance, or the current passing through the circuit, this one. You can see that effect here. You have this water film and all those things. If the water film is like this, you never get a failure. So if you look at here, this one is covering only this one. This one is not coming to this, because there is an inter water film boundary. There's an inter water film boundary here, there's a boundary here, there's a boundary here. That never leads to failure. Where you get failure? At a point when the water film droplet collides together, become connected between these two, suddenly you can see that dendrite is forming. So as long as the interdroplet layer exists like this, and then you never get the failure. So the cohesiveness together, that is important. You can think that, oh, this water film will form and coalesce together, and why this is. Yes, it is important, because what we are telling is that, again I go back to that statement which I made in the last lecture, that is, here the water film formation is a transient effect. That water film may exist only for 30 minutes. that 30 minutes, if you can make the water film like this, without having such kind of conditions, then you don't have the failure. So that's the reason, that's the importance of understanding. So now coming to the modeling, what you need is that here, the first level of modeling, we assumed that the water film thickness is average. You have a certain electrical property. So that there is something wrong in that. Because this electrical property, what we are taking here, corresponds to a particular thickness, is not correct. Because that's a combination of this part and this part. So we are trying to see that we can actually find this actual water film thickness here, and so that we can actually import that geometry into this modeling, so that we can actually say that in the model, when the water film is forming like this with an interparticle boundary, or if it's coalescing together, what happens, so that we can make a much better model in that case. This effect, whatever I'm talking about, this coalescing together, you can see much more clearly here, because here so you can see that water film is forming. It's a droplet is still small, so it's not connecting between the droplet, it's not coalescing together. Why can I go back? Oh, so you can go back. It's not coalescing together, but you can see that some point of time it coalesces together here, and then you get the failure. So that's an important part to put into this. So what we are trying to do is, we are still not over all these one. We can make we have the electrochemical model to calculate. We can say that such kind of structure we can import into our COMSOL model and calculate what will be the leak current, assuming that is water layer is uniform. But we don't have the model yet to calculate that is when the droplet is like this, what will happen. So what we are trying to do is that we try to take many pictures and they do the image analysis. So there are some mathematical equations we can say that when the droplet is forming like that, what will be the volume of the droplet, we can calculate from this diameter. Then that volume, if we calculate in an area, we can subtract and get a interwater film thickness layer. There will be an error in that, but at least to some extent, we can get that interwater film thickness layer. Then we can import that geometry into the COMSOL, so that we can make a much better model. Again, this model is not only useful for this, but you can think that any atmospheric corrosion case, this is useful. So yesterday I was talking about this, in the CCS condition, where there is a vapor phase corrosion, and I was showing you one cell which we made to the vapor phase corrosion. There also it will be forming the droplet like that, and there also such models can be applied there. You have something to? Yeah. Sorry? Yeah. I don't remember exactly, but these kind of things are probably 3 hours, 4 hours time. That's the type of experiment, maybe within that level. So that is one part. So then we can import this water geometry and we can make a better model. But then there is another issue. That issue is, as I told that earlier, that is we have this thing called hydrolysis. I think I don't have to go back. Hydrolysis part. So you have a part of the current is used for the hydrolysis. So we want to know that how much. So when you have this current here, this current is leading to the deposition, but not the whole current. So probably you get a current here, the leak current. Probably initially it was a 100 microampere. Out of 100 microampere current, entire current is not used for deposition. Part of the current is used for electrolysis. If you know that part of the current used for the electrolysis, then there is another thing in the COMSOL. Now we are modeling only the current lines. So that means that we can calculate the leak current between these two. It will not show the dendrite growth. But there is another thing in the COMSOL called growth model, where we can also actually say, we can see how the dendrite is forming. depending on the field here. But in order to do that, we need to know that what is the fraction of the current which is used for metal dissolution and what is the fraction of the current which is used for electrolysis. So we are trying to do some experiment which we combine the analysis with an electrochemistry together. So that means that we do an experiment like this, and when we are doing an experiment, we collect the solution at different times and measure what is the amount of metal is dissolved from that. And so this is what you see, that just a certain experiment. Again, this is in the initial stage. You have different times. You have different type of pitch. Pitch means that you are changing the distance between the electrodes. And then we know that each time when we take the solution and we measure the tin ion concentration by using the ICP, and then we know that how much tin is dissolved in each condition. And you can also see that there is a certain points we put ECM, and which shows that there is a certain level of tin concentration is needed for the ECM to occur, like that. But this is, I don't want to tell too much about that because we need to do much more calculations and things like that, all these. But what we can get out of this is, we know that how much tin is dissolved in the electrochemical process. We know the total current. Now from this one, from the total current and this one, we know that by using this information, what is the percentage of charge used for the tin dissolution, because we know the tin ion concentration. So that means that we can say the rest of the charge is used for electrolysis. So if I put a boundary here, you can see that approximately around 50% of the current is used for tin dissolution, and rest 50% is approximately used for the electrolysis part, which is an additional information into our model, so that in this model we can say, assume that 50% of the current is for electrolysis and 50% of the current is for tin dissolution, and that way then we can model better the information. But we are not there yet. I was talking about this contamination of the surface, which put a limit, humidity limit, because of the hygroscopicity. So when you have the contamination on the surface, which put two things are important. One is it put humidity boundary. It will determine that what humidity level you get the condensation, because it's hygroscopicity and deliquescence. Another thing is that when the deliquescence water film forms, it dissolved in the water film, it also determines the conductivity part, right? That's what determined that. That's the reason that you have seen here when we did this experiment. With one clean, you get a level of leak current. With one contamination, you get a level of leak current. Another contamination, you get a level of leak current because of the conductivity part. And other one is that it determines this humidity boundary because of deliquescence. And you can see here that these are the different flux system what is used in this manufacturing, and with the different types of activators in it, like adipic acid or this one. Clearly, you can see that there is a difference in the moisture absorption. If this absorbs less moisture, this absorbs more. This absorbs when we have a much more active acid, like hygroscopic acid, that absorbs more moisture. So that means that more water film is forming, and directly that also connected to this deliquescence, humidity level, and all those things related to it. And then you can see that when we do the experiment, you also get these leak current levels, which is also corresponds to this moisture absorption. So you can do this correlation and things like that. So we have done a lot of experiment just to show you a cross section of that is how that is, why that is important. So what we did is that now, like this is again, you can see that boundary to failure. So over the last 16 years, we did large number of experiments. So a lot of PCB structures we have tested over the last 16 years in different conditions. Like the pitch can be starting from 300 to 1000 microns, like that. Contamination level is 25 to 100 microgram per centimeter square. Contamination type, various type of contamination type depending on this chemistry, and voltage, different levels, temperature from 20 to 25 to 60 degrees centigrade. So we had a lot of data corresponds to all these conditions we had. So what we did is that we made a scatter plot out of that. So that scatter plot clearly shows the importance of All these what I'm talking about. If you look at here, you can see that there is a failed category and there is a non-failed category. Now, you don't have to worry about what is the type of parameter here. Irrespective of any parameter, what you see here is that if the humidity level is less than 70%, this leak current never leads to failure, electrochemical migration failure. Always, if the humidity level is lower than that, leak current what you get is lower than 10 microampere. And when the current level is lower than 10 microampere, that never leads to electrochemical migration. So that we can also say that the cutoff limit for this leak current that is causing the electrochemical migration is 10 microampere. As long as you can limit the current during the condensation period less than 10 microampere, you can avoid that is forming the electrochemical migration, for example. Another thing is a humidity boundary. Humidity boundary, you can process the PCB with any way you want. Only thing is, if you can keep the humidity level lower than 70%, you never get the failure. Of course, if the PCB is made in a nice way by using good flush system with a less hygroscopicity, you can go to here. So this is an average with all contamination type, what we are talking about. So that's really a very good information for the companies. That, for example, like they knows that what is the cutoff limit from the current point of view, what is the cutoff limit from the humidity point of view, and things like that, which is also coming from a lot of test data. Just to tell another thing, that is another type of failure, which is a conductive anodic filament. I mentioned that happens inside the laminate. That's because sometimes this PCB is multi-layer. If you look at your mobile phone, the PCB thickness is probably 0.5 millimeter, but within that 0.5 millimeter, probably it has 30 layers. 30 layers like this inside. And that means that many of the conduction lines are inside the laminate so that they can put more component on the top. That's the idea. Now you think that this polymer is permeable to water, water is going inside. So there is a water within the polymer. Within the polymer, there is a water between these two. This is a copper line. That's a copper line. There's a water between these two within the polymer. So that's what I mentioned, that if you have that situation, copper will be dissolved like this. That copper will form copper hydroxide. If there is chloride in the system, why there is chloride in the system? Chloride is normally avoided with all the PCB manufacturing. But this one is glass epoxy polymer. Epoxy always contains some chloride as a part of the molecular structure. So that chloride is some amount of, very little amount of chloride what we are talking about, that dissolved. Then this also can convert to copper chloride. This copper chloride and copper hydroxide mixture that forms, and when it forms more, it will be pushed and pushed like this, and then you make a conducting bridge. That's what is called the conductive anodic filament formation, which happens inside, and then you get the burning of the PCB again. Now, the industry is ending up with another problem with high voltage, which we need to understand. Earlier, the pathway for this one is like this. The reason is that there is this glass fiber, and that is the interface at which it is easy to move. And this movement is also connected to the field. Now with the high voltage, what people are worried is that you can have this one formation from one layer to another. And they call it as vertical. So this is horizontal conductive anodic filament formation. Now they worry that because of the high voltage between the layers, you can have a vertical formation of CAF. And that is much more dangerous than this, because these layers may have some typical power and things like that. So the vertical formation is much more dangerous than this one, which is nobody knows exactly how it forms, and this is something which comes with the high voltage and experiment and like that. I just want to show you one failure also related to the integrated circuit, because that's another type of combination, material combination that happens. When you take the integrated circuit, If you look at the inside the integrated circuit, this is what you see. This is a silicon semiconducting part. So this semiconducting part is divided into different layers by using these aluminum lines. So all these are aluminum lines, conduction lines, dividing the silicon semiconductor. Then this one has to be connected to each of these aluminum lines has to be connected to this one. This is the one which is then coming to the PCB surface. So this connection between this one and semiconductor is done by using a gold wire. This gold wire here is joined to this aluminum pad. That's what you see here. This is a gold wire. This is the aluminum pad on the silicon substrate. So that's the way it is joined together. And that's because this one is done by the ultrasound vibrational bonding. So gold wire is easy to bond and things like that. That's the way it started doing that. But the problem is that now the ICs are integrated circuits are used in much more heavy applications with automotive, with a heavy environment. When the environment is going inside, that's not a good combination, right? Electrochemically, that's not a good combination. And in addition to that, there is also another problem, that is between gold and aluminum, you can form a lot of intermetallics between gold and aluminum. That means that during the welding process and after the welding process, when the IC is using, IC temperature can go up to probably 80 degrees centigrade, heat up, self-heating. Slowly, these intermetallic particles will grow at the interface. What's the problem? These intermetallic particles are brittle compared to this bond. So when the intermetallic forms, there is only little bit of corrosion, it becomes a fatigue failure. So this is the issue. So corrosion becomes very little corrosion is enough to get a fatigue failure and the debonding. So this is the issue in the integrated circuit, and slowly all these integrated circuit manufacturers are looking into replacement for the gold. Now they are trying with the copper wire. Copper wire has certain advantage compared to that of gold wire, and but it's not totally solved the problem like that. People are trying with different this one, but we will not go into that. But I just show you a little bit on that. This one, like so, this is a bond. You can see here the gold wire is bonded between these two. This is silicon die, and this is the bonding what I'm talking about. That's what you see here, which has corroded around that because of the galvanic coupling. But you can understand. So I just show is this one. So that one of the gold wire I'm showing here, which has debonded and the gold wire has gone. And that's the actual case. That's what I just want to describe to you. That is why this has happened is, this is a case with Bosch, for example. Bosch had an integrated circuit like this. So that particular integrated circuit has to be a little bit open because it's a sensing device. Sensing device means air has to come to the surface of this IC. So you cannot totally package that. And then this air is coming, and suddenly they found that all this wire bonding is breaking. And this is also an example of how sometimes a polymer can contribute. And they don't know why this is breaking. This bond is breaking, and they didn't understand that. And that later they did a lot of analysis, and we were also involved. Then they realized that the problem is that this IC, it's an automotive thing, IC is there, and then this things has to come to this IC to analyze. So this IC is covered with a polymer tube. This polymer tube is made of polyamide. In the polyamide, you use the potassium iodide and copper iodide as a stabilizer. With the moisture coming to the polyamide surface, this iodine is coming out, and this iodine is as a vapor is coming out, and iodine is mixing with the water and forming hydroiodic acid, and this hydroiodic acid is going and corroding this bond wire. And when the bond wire is corroded a little bit, as I mentioned, it just debond. So we did a lot of experiments to try to understand that is how this this is occurring. So that's why instead of taking the wire bonding, we took a very simple system where you have the gold coating, aluminum coating like that, and then we do the heat treatment. So to create these intermetallic particles in between these layers to mimic what happens at the interface. So this shows this is the this glow discharge optical emission spectroscopy is sputtering to see that how the intermetallic layer is forming. So otherwise it's not that important there. So then we grow these intermetallics, and so this is just showing the SEM picture once the gold and this aluminum is mixed together, forming the intermetallics, and then we do, so while forming the intermetallics, we do the in situ HRD. So we can do the in situ HRD at heating at different temperatures. So while doing the HRD, so we can follow how this intermetallics is growing at each temperature. And then we did the electrochemistry. So when we did the electrochemistry, what we also did is that in addition to doing the electrochemistry of the surface, we also made, Bosch also made the actual intermetallics by, this induction melting and all. They made the actual intermetallics, and we also did the electrochemistry of that. And then that way we could clearly understand like what is, and everything what we studied in this potassium iodide solution, and so that we can understand how the iodine is affecting and all those things. We also did this taking the actual component, exposed to the iodine vapor, and with the humidity together, so you can clearly see that effect. So if you have a control sample, so basically when you have that wire bonding, how you determine the strength of the wire bonding, because you do a shear. So think like this, you have a shear tool and see that how much force is needed to remove that. So then you can see that when we do one is the heat treatment, and then you can see here that is one is we do the heat treatment at different levels to create the these intermetallics, and then you can see that with different humidity level, the shear force is coming down. Basically because as the intermetallic is forming and this humidity is there, and together with the iodine, then you have the corrosion, and this corrosion is occurring at the interface, and then you have the lower and lower shear force, for example. So that's an example of like how a polymer can sometimes interfere and create a degassing, and then you can go and corrode the this bond wire and create a problem. That's just showing that what is the mechanism of this one. Iodine is coming out of the polymer, then it is forming hydroiodic acid and then reacting, and there is also then with all these reactions, iodine is again regenerated, so that this is a kind of an auto catalytic process sort of thing. And it is exactly similar things happens with this kind of high power devices, because you have the similar bonding here in the high power devices. So it's a similar thing what we are talking about there as well. Now I mentioned that, for example, we are talking about this internal part. So I told that is also equally important, this packaging. So if you know how to put a good packaging, that way you can put a damping of the humidity going inside, and that way you can also do a lot of things. We also work in that area, but I will not go into detail, except to show that like how we are approaching all these together. That is intrinsic to extrinsic to intrinsic. So we have the climate transfer function, climate model we created. That I'll show you a little bit, because we have a climate app. So using the climate app, so we can simplify the climate from a place, so that we get a easily we can make a profile corresponds to a, for example, if you take the entire world climate, there are many climate zones, climate profiles, right? But instead of that, we combine together, so that all these pink color what you see, it is like we can make a one profile. So once you make that profile, we have our CFD model, and in CFD model we can put any geometry of this packaging. We can assume that there is a PCB inside, and all those things we can describe. Then our CFD will calculate if this climate is applied to such kind of bots, what will be the humidity buildup inside over a period of time. Once we know that, then there is a condensation model, and the condensation model will calculate whether there is any, depending on the condition of the PCB, whether there is any chance for condensation. Once there is a chance for condensation, then this is what I was showing you earlier. Like we made the electrochemical model. That electrochemical model will calculate which area is more prone to this leak current and things like that. But this is not a perfect model. But there is a model, but it's not a perfect model. That's what I was mentioning earlier. We need to put the geometry of the water film and all those things. But this is the way we are approaching. That means that if we integrate all these models together, we can start with a profile they want, feed into CFD model, feed into condensation model, then use the electrochemical model to calculate what is happening. we have all these models. We have this model highly developed. We have this model highly developed, which is already we have like an app which we are trying to make it as a commercial product. Partially developed condensation model, there is a lot of work to be done more. Partially developed, we can calculate the leak current, but geometry of the water film and things like that, we are still not there to put it in a correct form. So that's where we are. If you are a little bit more patient, then I'll show you this app. So in the meantime, it comes, we can little bit tell what we did here. You know that in order to do this, first we need to get the weather data. So all airports in the world collect weather data on hourly basis. And this is freely available. Everybody can get that. And there are about probably more than 10,000 or 20,000 airports all over the world collect this data, which we can get freely. And it is also the 1 hour period every day. So it's very good. So 24 hours means really you can get the profile, that one. So we collect their climate data, and then we use the machine learning algorithm to collate the data together. So we can ask the question by this machine learning algorithm, we can specify saying that one of the things it has to look is humidity level more than 95%, say, and that humidity level exceeds more than 1 hour. Then we can say that put together all the climate in the world where the humidity level goes more than 95% and say period more than 1 hour. You can also specify that how many days or some whatever parameters, then it collate together like that, identify, collate together. And there are many, I'm a little bit simplifying it, and there are many things, and that way you can get you can put the climate together and make this different zones. So what it shows that is like whatever parameter we asked the machine learning to look at it, and that way all these purple color region has a more or less similar conditions. Yellow color region has a similar condition, green color region has a similar condition. So with that, what we did is that this LMAX zones, what we call it as, this and all will be changed in the commercial, this one. LMAX is our project name. So since we made in the project, we put it as LMAX, so it will change. So we made that into 8 zones now, and that's what we did. And that's what you see, these 8 different colors here, and that means that we can say that from this we are making an average profile. We can, the entire world weather conditions, we can change it to 8 average profiles like that. Of course, average profile will not represent totally each of this climate in that zone, but it is something which is better have, to have rather than taking everything into together. So that's what we did. And then we can collate this data together in different ways. So if you take the LMAX zones, now what we see here, this is collated with the thing, with the thinking that what is the chance for condensation. So that means that in this particular case, we asked the question, if the dew point temperature and the actual ambient temperature, if the difference is 1 degree, 0.1, if that condition exists more than 1 hour, condition 2, and based on that, you collate the data in one case. Another case, if the dew point temperature difference is 2 degree, 3 degree like that, and that's the way, based on the dew point temperature difference, that shows a condensation chance. That is what is did here. But instead of that, we can have day type zones, for example. So that is another way of collating. Day type zone means everything is, you can see here, that is day type zone is a little bit, day type zone is based on the scatter plot. So we had around, think that around 20,000 stations we have collecting the data. That 20,000 points is put here with a temperature as the x-axis and relative humidity as the y-axis. Now we can see that that is divided into these different boxes here. So you can see here that is like, so if you look at here, this box, that box has a, I need to take it up, temperature range within that level, and humidity level in that box is between these. So that's a very, if you take that box, that's a very heavy a region where you can have a lot of problem, because it has always there is a humidity level more than 95 to 100% and with a certain temperature like that. So then we say that group together those climates like that, and that way we can say that day type means that depending on the humidity and temperature conditions we can collate together. So sometimes you want that, so you can decide that people who are using this map, they can decide how they want to collect the data. And you can also get a little bit more additional information. For example, take this one. You can get the mean profile for these zones, but more important, this one, what I want to show here is this one. So earlier I told that we collected with dew point temperature, and just to show you that how this is useful. Now that dew point temperature collection of data, we took this kind of map from that. So that shows that take the zone 8 and zone 8 and take this triangle, these circles which has TOW1, what means that all these circle points shows that the temperature difference between the dew point and the actual ambient temperature is 1 degree, very high chance for condensation. So this graph shows that if you take extrapolate here, almost in this zone 50% of the days in an year, there is a chance 50% of an year this condition exists, where the dew point temperature to ambient temperature difference is 1 degree. 50% is a very big number. That means that this is a zone where we can expect a lot of condensation. Compared to that of, if you look at this zone, it's only less than 10%. So it gives a lot of information for designers and things like that. And so that's the reason that we are trying to make it as a commercial product, so that those who are working in corrosion, those who want to understand corrosion, probably they will use it. There's an additional thing in this, that is we also put population density, because this is sometimes a useful information to know. Another one is these stations. No, that is stations which is showing where from we took the data. You have this you have this corrosion data which are showing that, telling about the atmospheric corrosion. So there are atmospheric corrosion test sites all over the world, and we took that data and overlapped on this plot. So if you just open one of them, you can see that this is in a place in Norway. There is an atmospheric corrosion test site, and that place, the steel corrosion level is this much, and SO2 and Cl deposition and all that kind of information also you can get. So it's not just humidity data, but you can go to specific point where there is this atmospheric corrosion test site, related data, so you can see the corrosion class, and that information also you can get. Now the next question is that by using this corrosion test data at different places, again you can use this program to interpolate and things like that. That is different things, but that's what we have, and we are trying to see that whether we can make it a commercial product and sell it. Now it is like an app, so it's already like in a product which our partner companies are using it, but it's just with a little bit of changes we can make it a full product sort of thing. Yes, I think that's the last thing I want to say. Now we can go to the questions.
In normal corrosion experiments, from the EIS we will fit circuit, electrical equivalent circuit, we will get the circuit elements. So we are not worrying about any current. So here from the EIS, leak current you are getting from EIS test?
Leak current is from the DC experiment. So I didn't go to the details. If I say in detail, there's a little more in that. So what we do is, we cannot do it in one go, both. You can do it, but then you will not get accurate result. So what we do is, in one experiment, we do the water film thickness measurement and one of the electrical property. Then we repeat the measurement, and then we do the impedance measurement. We not combine. We can do the combined way, but then what you have to do is that if there is a 2 volts DC, and then you have to apply the amplitude over that. which we found that it will not give us accurate results. The idea behind this one is impedance result should only represent the water film formation, shouldn't have any other electrochemical thing in that, and this one should show fully the electrochemical part, that is whatever corrosion is occurring and things like that. So that's the reason that we do this this separately, and we made sure that when we repeat the experiment and we get the same behavior in that equipment.
Electrochemical elements
Yeah.
in the circuit. This PCB circuit elements also there in the circuit. How we can model?
Yeah,
equivalent
that
circuit?
in this case is not there. In this case, it is only 2 layers, right? 2 electrodes. But you are right. That is, for example, if we are doing this experiment on a resistor surface, then we need to consider in the circuit that is that resistor value. But then we know that resistor value.
Reality, we have to perform the experiments on resistor and capacitor.
No, because we know the resistor value. See, if you have a I think this is what you are asking. If you have a component like this, we know the value of the resistor. That's not a problem. The problem comes if you want to do the, like, I don't know where it's clear to see. Yeah, maybe I can show here. The problem comes if the problem is between these 2 legs. That's like a surface in this case. But in this case also no problem, because then it's only a water film. Like that was like my PCB. But whenever we have a component which is involved a capacitor resistor, we know the value in that. So we can put that into the circuit.
We can include these elements into that data.
Yes.
Whatever. Circuit.
Actually, this comes to another thing. This is what I was talking to ANSYS people, because one is that we can do the electrochemical model, which I showed, assuming the water film. Another thing is we can do the circuit model, which is like a impedance fitting. Circuit model is like, when the ANSYS, when they design this PCB, they have all the circuit diagram. And circuit diagram is showing that this resistor is here and all those things. So actually in the circuit, they can say that this area water film is forming, which means that circuit will assume that if you give the electrical property of that water film, there's a parallel resistor here. If there's a capacitor, there's a parallel resistor over the capacitor. And that circuit will be able to analyze what will be the implication of that. It's like a impedance which you mentioned. Only thing is we are doing at a little bit more a bigger scale. So ANSYS program is used for the circuit design and things like that. And so I was telling ANSYS that because we are now all these electrochemical model we built in COMSOL. But the problem is that many of the electronic companies, they don't use COMSOL. They use ANSYS. So now we are in discussion with the ANSYS that some of these companies want to transfer our model to ANSYS. So I was telling ANSYS that they can actually make a product where you can use this electrochemical model product. They can also do a circuit model. So you have the whole circuit, and then this PCB design people will be able to say, on this PCB, this is the sensitive area. That they know from the circuit. That is, this area should have a very high impedance. So any stray current in that area is problematic. So then they could put this, we can provide them the water film characteristics, electrical characteristics, they can overlap that and say that, okay, if the water film condition is like this, and what will be the level of stray current and how that will affect. Yeah. So one is that as we can put that component to the impedance analysis, but extending that, there is also a possibility of doing this circuit analysis with that concept.
Dendrite formation by in situ experiments we are observing, or after formation taking to sample to SEM or optical?
It's both. We can, most of our experiments have a camera when we do, because this is very important so that we can study all the growth and things like this. So for example, like these images what we are showing here, right? Somewhere. This one and all these images what I'm showing is in situ. This one.
Length scale within, it is in micrometers range, sir?
Sorry?
Dendrite length scale.
Yeah. This, I'll tell you, this distance here, is that what you're asking? In this case, this distance between these two is, I think it is 3 millimeter distance. So we use the camera for experiments, and for example, when we are doing this experiment as well, we can put a camera on the top here. So you can see there's an opening here. So we always use a camera so to record, but we don't get a higher resolution. We can get only this resolution. Then we take this sample after that into the X-ray diffraction or to the SEM. That's after experiment.
This temperature we are reducing by passing some liquid nitrogen, or how?
Yes. No. It is cold water. See, for example, in this case, there is a heat exchanger sitting below. That heat exchanger is connected to a coolant. Just cold water. We are producing the cold water in another system, which we can control the temperature, that we pass through the heat exchanger, and then we do that. We can also do that, even you can also do that by without having a this heat exchanger, by using a Peltier stage. So the Peltier stage you can buy, and so that then you can, one side it becomes hot, other side it becomes cold when you pass a current, and then you can put on the top and do it. Only different problem is that Peltier stage has a limit of temperature drop you can get. In this case, you can you can change the temperature of the PCB from 20 to 5 degrees centigrade. So that's the advantage.
Sir, in ceramic board, is it made up of ceramic composite or it's pure ceramic?
No, it is simple alumina.
Simple.
It's just alumina, like the things, white material which used for the furnace and different things like crucibles and things like that. So it is just alumina. Ceramic board? No. Ceramic you cannot have multi-layer. It is only single layer one. The only thing is that they make that one. You will see only, if you get a big electronic equipment, maybe you will see only a small part of it is like that. That is specifically because it can withstand higher temperature. So wherever it is required, just for that power module, they make it like that. So it will not be multi-layered. No, this hydrophobicity and things like that is a myth when it comes to long-term issues. And there is a company called 3M, and 3M always supply a hydrophobic coating to electronics, and people use that as a spray, not spray, I think it's a dip coating, I think, on the surface. Of course, it's a dust protection, but it will not work. It's a porous layer and things like that. All these are a myth. Hydrophobic coating. It is certain cases, some limited application, but not for the PCB. I just want to show you that this one I was talking about, this diode failure. You see, this is a diode package, which is packaged in this is epoxy. Of course, it's permeable to moisture. And so this was on a PCB surface, and it just took the moisture went inside. When it goes inside, this is the inside structure of that one. So you have an electrode here, and a semiconducting part here. So it will allow the passage of current only in one direction. So you need to take that as one of the, say, positively biased electrode and negatively biased electrode, like that. So there is, in order to join the semiconductor to this, they use a solder material which contains silver in this case. So you can see that in this picture, the silver has from there has migrated like this down, and then you get an electric short inside, and then it blow off because of the voltage, and that's what you see in this tomography image here. So this region, so that's the way it happens. Many examples are there like this. So in this case, only the difference is that it's not directly exposed to humidity. Because they didn't use a slave pump, there was condensation. This one was saturated with humidity, because polymer is like a sponge, right? Saturated with humidity. So inside, somewhere along this interface, a water film has formed. There may be a gap between epoxy and this. It will not be a perfect interface. So somewhere that interface, a water film has formed, and that caused that. If you want to protect electronics from humidity, it's very easy. It's not a difficult thing. That I think yesterday I was saying, right, like all these solar energy systems, solar energy where there is these converters and inverters sitting, and the problem is in the night time, you can do a little bit of heating in the night time, and if you calculate the energy what is required for that is very little to keep the temperature slightly high. But the regulations will not allow that. That is, the European regulation says that you are not allowed to heat any electronic equipment. You are not allowed to spend energy on any electrical equipment when it is off, because that's not a climate-friendly green solution. They are not calculating that if that heating will stop the failing of many inverters and converters, so that way more sustainability comes from that. But they don't think like that. They think just from the energy point of view. So that's a typical example. So many of the actions are either it is like this because of the regulations is a problem, or it is because of the costly. Inert gas putting and all is become very, very, very costly thing.
Only we at critical time, whenever condensation is happening,
Yeah.
that time only we have to create inert atmosphere.
Yeah, but you need to think that it is like these electronic things are not used. For example, a wind turbine is a place where a lot of electronic equipments are put together. Think that there you can have a dehumidifier, you can have a inert atmosphere or whatever. It is much more easy to implement. But what do you think about power electronics sitting in the in this mobile antenna everywhere? And with 5G, you need to have these antennas much more closer, right? For the 5G. Earlier with the 4G and 3G, you can have a very much separated antenna. But now you need closer antennas. So that means that number of electronics sitting in that is increasing. And which is directly sitting there. You think that there is you can have inert atmosphere and things like that. So even the solutions what we can do is certain places we can implement some solution, but other places that are not possible. So it's not a viable option. Yeah. So all these mobile antenna, what do you see? There is a lot of power electronics sitting there. And there is a company called, which is also part of our consortium called LTEC. LTEC is a Norwegian company, which is a part of the, there is a big Taiwanese company called Delta. So here I think this company is known as Delta when they supply the electronics. And in the European side is called LTEC. And they are making the whole power electronics, what they are making is for the data centers and mobile towers. And there are so many mobile towers in India. Everything is exposed outside and they get all the time they have the problem. And there it is not easy to protect like that. So they do the coating. In that case, they do the coating. That is, they do the polymer coating. But when they do the polymer coating, then there is an additional thing. That is, you know that, right? Think an aluminum surface. Aluminum surface is totally contaminated with the chloride. Is there any point in putting the paint? So similar thing, if the PCB is contaminated, there is no point in putting the coating. So what they need to do is, before coating, they need to clean. So that's what they do in the aerospace. Aerospace is, want to make it very safe in all the electronics. So what they do is, they don't use, the first thing is they don't use a new process, which we call it as a non-clean process. They go for the old process where they can do the soldering and then there is a flux is remaining on the surface and they can clean it. So they clean, not one time, but 2-3 times they clean the PCB, and after cleaning, they coat it, and then sometimes they pot it. So there's a coating, and then probably sometimes the entire equipment is filled with a polymer, so that they can make sure that nothing will happen to the electronics there. That's because they are not worried about the cost. You cannot have that in a, in automotive. If Bosch want to make a control unit, automotive people will wants to get as cheap as possible. Bosch cannot implement that kind of solutions. They have to work with non-coated PCBs. Maybe some cases they can coat it. They need to work with this packaging, which is semi-hermetic. So all these are the realities for them. So they have to work within that boundary conditions and make it perfect. Tesla is, again, Tesla, why Tesla may be having some electronic failure, but you don't see so much in Tesla. Why? They use aircraft technology today because the cost of Tesla is that much. But if the cost of the Tesla has to come down, they have to move away from the aircraft technology. Then you start getting the problem. Then if there is more, of course, we'll be discussing in the afternoon anyway, right? Then let us break for lunch.